I want you to pay attention to what I'm about to go over. Now, there's some confusion at times in the book about this, but I want you to pay careful attention. And I get questions about the quiz. All right, it's on the H field. I mean, it's not going to be on E field or B field. That's what it's on. So let me go through some things, and I want to make this crystal clear to you. All right, this is important. Now, the standard canonical, the classic current distributions, infinite lines, loops, or planes, you have to know the H field from these things on the axis of, say, on the z-axis if it's a looping xy plane, or from any kind of line of current, or any kind of surface current density. So I want to go through the one that's most confusing right now. I mentioned it before, and I want you to pay careful attention. You know, if you have an infinite current, it doesn't matter the direction, magnitude I, and you want the H field at any point, the important thing is the perpendicular distance, rho. Now, rho does not have to be measured in cylindrical coordinates. In general, it's not. Dr. Wentworth's book does not make that really obvious, but I want to make sure about that. It doesn't matter about the coordinate system. It has to be perpendicular. If you want the H field here, the equation is it's really I over 2 pi rho. Now, rho here is going to be the magnitude. Y'all follow me? Then there's a, he calls it a phi. That is just, it's really something that's like, this current is going to be circulating around the wire's axis. It's in the phi direction if it's on the z-axis. Do y'all follow me? But really, a phi has a different meaning. So the way I do this, and I did it last time, but I want to really make this clear. Listen now. If you have a current in the z direction, you have a unit vector AI pointing in the direction the current is going on the axis if it's an infinite current. Does everybody follow me on this? Now, you also have a unit vector pointing in the radial direction. And a rho is simply is really going to be rho vector over magnitude of rho. Y'all follow me, class? Magnitude of vector. I'm going to do an example. Does everybody follow me? Now, from that, you can get a phi, and that's equal to AI crossed into a rho. Y'all follow me? So I'm going to do an example. Remember, rho in this case doesn't have to be measured from the z-axis. It's the distance from the perpendicular point to the point of observation of the H field. Everybody got that? And AI is a unit vector in the direction of propagation, or the direction the current's flowing. Now, I'm going to give you a problem that will help you understand this clearly. There was some in the book, but I'm going to do this one for everybody. Suppose I have, call this the x-axis, call this the y-axis, and this, this will be the z-axis. So this is a little different kind of a, you're used to having z up. Y'all follow me, class? It's still a right-hand coordinate system. Now I'm going to say this. I have a current on the x-axis that's infinite. Y'all hear me on this? I'm just going to assume a current. Doesn't matter what it is. I'll call it Ix. Now I want to find the H field at some points. Y'all hear me? First point I want to find the H field at is going to be the point at 0. No, I'll call it this. I'll say it's 1, 2, 0. So I want the H field. The point, the first coordinate would be X. Second coordinate Y. Third coordinate Z. Y'all follow me, class, on this one? Everybody got that? So locate the point. Try to draw it as best as possible. Well, X equals 1 would be here. Y equals 2 would be here, actually. And you all see this. So this is the point I want the H field. It is at Z equals 0, right? Now here's where people make mistakes. Remember, I said rho is measured from the perpendicular distance to the point of observation. Y'all with me? And it is a vector. So on this one, when we look at rho, take a look at this. the x coordinate doesn't make any difference. It's an infinitely long current in the x direction. Do you all follow me? How many see this? Forget about the x. Look at the perpendicular distance, the rho. You all see that that's going to be 2ay. How many do? And z doesn't matter, right? Where z is 0. The line on x, if you have an infinite current on the x-axis, z is 0. So it's really going to be 2ay. Everybody got that? Now, what is the unit vector in the direction of current, class? Unit vector. Class? Just ax. Do y'all follow me? Ax. So, when I write down what the h field is there, the magnitude will still be I over 2 pi rho. You all follow? So it's going to be I, which I call it Ix. It doesn't matter what it is. Over 2 pi. What is rho? Rho's a scalar, class? How far away are we? Just answer. It's just 2, isn't it, class? How many see this? You can just take the magnitude of the vector. It's 2. So it's over 2. Now, what is a phi? We'll do it right here. Well, it's ai, which you said is ax, right? Crossed into a rho, which is, oh, I didn't do this. What is the unit vector a rho, class? It's rho vector over rho magnitude. Can you all see it's just ay? Give me a show of hands if you can. With me on that? Everybody see it? It's just ay. So what happens? I have ax crossed ay, which is az, right? That means for this example, this, when you do this, is simply going to be equal to az. And it would be amps per meter. Now, if you look at this, it should make sense. Remember, I think I said this with the right-hand rule last time. If you have, take your right hand, put your thumb in the direction of current, for an infinite current, your fingers will curl in the direction of the h field. You'll notice out here at y equals 2, z equals 0. It's coming right out of the board. Can you all see that, class? It's az. Can you all see that? When you do more and more of these problems, you'll be able to see what the h field is without going through this formula. This is the way you do the formula. So that's it at 1, 2, 0. Now you tell me, I'm going to come over here and erase this. So what would happen if I had this same current configuration, but instead of wanting the h field at that point, now suppose I make this 1, 2, 3. All right? And get rid of that. We know it's going to be rho, and this is going to change. It's a phi, but we're going to do this as a class. I think this will really help you. All right. So you all agree the current is still Ix, right? I'm just assuming it has a current Ix. Everybody follow me on this. All right. The 2 pi stays there. Now we need vector rho. So this point, 1, 2, 3. Well, x equal 1 would be here. Y equal 2 would be here. And z equal 3 would be out. It's not easy for me to draw this, but this is where we want the h field, right? At that point, you can kind of visualize it. Y'all follow me, class? You can just show yourself. Everybody with me? So I need rho for this one first. So rho is the perpendicular vector. Remember, the x component doesn't matter in this case. Y'all with me? Because it's infinite in the x direction. With me on this, class? All right, so what is rho? Vector rho. Well, you take the coordinates of the point of observation minus the source point where the perpendicular line is and subtract them. Do you all agree with that? So x doesn't matter, but what about y? You get 2ay, right? Plus 3az. Do you all agree with that? How many see this? Just do it in your head. I mean, force yourself to think about this. It's not hard to see, but people oftentimes don't see this. They're a little uncomfortable with it because they're used to thinking that rho is just measured from the z-axis, and a phi is always the unit vector. In this case, it means something different. That's the one. Yes, sir.
In this case, x doesn't matter because the current is on the x-axis.
Yeah, well, you know, if the current's infinite, remember, you're measuring the perpendicular distance. So it doesn't matter where you are in x, the perpendicular distance will always be independent of x. Y'all see that? In the back? With me? All right. Now for this one, what is a rho? Class? Technically, it's what? Over magnitude of rho, right? So you just repeat the vector 2ay plus 3az, and then you can square both components, take the square root. So you get 4 plus 9 is 13, square root of 13. Everybody with me on that? Now, what is a phi? Well, remember up here, right? So for this one, it would be a phi is what? AI is still what, class? Say it. AX. It's crossed into that vector. Now I have two components. I'm going to take the square root of 13 out in front. And it's crossed into 2ay. And it's plus 3az, right? Now, if you do that, what do you get for a phi? Well, you're still going to get 1 over the square root of 13 no matter what you do. I have x crossed y is z, right? Az. So I have 2az plus x cross z is minus ay, correct, class? Make sure you know. Somebody see this right here. So it's going to be minus 3az. Now, if you look at this, sorry. Here's what? Thinking ahead. Sorry. Y'all with me, class? Now, if you come to this point and we go ahead and write this equation right here over here, I'm going to put it right here. I have h at 1, 2, 3. It's ix, whatever that is, it doesn't matter. It's over 2 pi. And what is rho? It's a magnitude, right? Just square root of 13. You all see that, class? How many do? So it's divided by the square root of 13 here. The 1/2 power. And it's times that unit vector, which has got 1 over the square root of 13 in it. So actually, 1 over the square root of 13 times the square root of 13 is just 13. And then you get 2az, right? And you get minus 3ay. And lo and behold, that's it. How many see this? I'm going through it methodically so there's no mistakes in the concept. I don't want to fly through. Everybody follow me? I hope this helps some of you that have questions about this. This should clear it up. You with me? Now, what happens if you have two currents? Suppose I have a current in the x direction and a current in the y direction. And I want the H field at a point. How do you go about doing it? Just in your own words, class. Well, you superposition. You find the H field from the first current at the point of observation, correct, class? Then you add to it the H field from the second current at the point of observation. Let me finish my thought here. I'll get to you in a second. And I want to show you just some obvious, if you have insight, you'll see this in a heartbeat. So now, if I had something like this, I'll try to draw this, right? I'll call this X, call this Y, call this Z. And what I'm going to do is this. I'm going to put a current of 1 amp here in the X direction, and I'm going to put a current of 2 amps here. Infinite current, so it's going this way. I didn't show you that way. Just 2 amps there. 1 on the X, 1 on the Y. Y'all follow me? Y'all see this? Now, if I wanted the H field right above here on the Z-axis at a distance of 1, where this would be 1, and I wanted that H field at 0, 0, 1, what would it be? And think about what I've told you about the right-hand rule. Can you all see the current from the y-axis here? It's infinite, right? I'm only 1 meter away, right? Can you all see, if you use your right hand, it's going to be pointing in the x direction at that point of observation. How many see that? You see it, Jim? All right. Now, what's the value from, this is for the one on the y-axis. The H field at this point, well, it's going to be 2, right? Because that's 2 amps, over 2 pi. What is rho, class? 1, right? That's the, I don't know. You don't be afraid to say, I mean, I'm trying to get you to participate. You'll actually retain more information if you interact. So it's just 1, which is a great number. And then it's in the A x direction, right? That's from this one. I'm just showing you how to do this. It really breaks down easily if you see this. What about from the one in the x direction? Now, use your right hand. Put your thumb in the direction of current. At this point, which way is the vector pointing for the A field? Class? Minus AY, right? So we know it's going to be minus, and it will be AY. Now what's the value? For that one, I have 1 over 2 pi, and what is rho? 1. Can you all see that that is pretty straightforward, right? You can write the mathematics for this, but that's what's going to happen. And a lot of times, just an understanding of the basic stuff. Anybody here speak German? I have a student. It's called Fingerspritzung in German. You get a feel for it, you understand what's going to happen because you understand the physics and how things are mapping. Things like this. Y'all with me on this class? Now, your question?
I was asking you.
What's it? All right. Now, do y'all follow me on this? I'm trying to be as clear as possible. All right. What I'm going to do today before the quiz, I want to go through something that I think you'll really appreciate. You remember how back in the day when we had Coulomb's law to calculate the electric field? Y'all remember that? Q over 4 pi, really dq over 4 pi epsilon naught r squared in the bottom. AR vector would be the electric field, differential electric field from a charge. You would integrate that to find the total electric field, right? Likewise, when we had the Biot-Savart law, we said dH was equal to IDL, right? The differential length of current, crossed into, or really IDL crossed into A rho over 4 pi rho, and we got the differential H field from a differential chunk of current. We'd integrate that to get the total H field. We did that for the loop and the wire. Do y'all remember? All right, now, do you remember back when you had electrostatic, or when we were doing the electric field, how Gauss's law was so useful if there was symmetry because it reduced the complexity. You had none of those crazy integrals. If you saw symmetry, you could use Gauss's law, and you could calculate very accurately the D field, right? And then you can get the E field from that. How many remember that? Right? That's the benefit of Gauss's law. Here we have something called Ampere's law that will allow us to do the same thing for the magnetic field calculations, but it'll be for a current, and I got to show you what it means. So this, I don't want to go too deep into math right off the bat, but you'll appreciate this. And the reason is because you can do the problems we've been doing in instant a lot of times. Just by, very simple. All right. Next. This is going to be Ampere's law. Now, Ampere was one of the fellows long ago that figured out a whole lot of things about magnetic fields. And he did a great job on a lot of this. James Clerk Maxwell took Ampere's law and took really the electric field equations and he combined them into one called Maxwell's equations that we'll get to. So Ampere's law is this. In a differential form, its curl of H is equal to J. Again, J would be a current density. Y'all with me, class? Now, this is the differential form. It parallels divergence of D is equal to rho V. Y'all remember? This was Gauss's law. That is Ampere's law. Y'all with me? Remember, for this one, what happened is the integral of D dot ds over the closed surface was really the charge enclosed, right? Remember that? Over here, if we integrate this, and I can just tell you, you can integrate this over a surface ds, but what you end up getting is that the integral of h, this is with Stokes' theorem, h dot dl around a closed loop is equal to I enclosed by the loop. Now, I've got to explain this in more detail. I know you've seen this before in physics. I mean, remember at least seeing something like this in physics. Hopefully you all do. All right. You've got to understand how to apply this. This is a very abstract form right there. The integral of h dot dl around any kind of a loop, a closed loop, will give you the current inside. Normally what they do is take curl of h dot ds and they integrate over a surface where current's penetrating. And they'll say the integral of curl of h is actually equal to the integral of h dot dl. Now, write this down, it's important. This is always in the counterclockwise direction. You always have to do that integral this way, counterclockwise, and I'll speak more about that in a second. Now let me show you. Use this when there's a high degree of symmetry. Probably the simplest and best example is an infinite current. So if I have an infinite current, I'll put it on the z-axis. And I'm going to have a current I right there on the z-axis. And I come out a distance rho here. Now, we've been talking about this already. Now what I'm going to do is make a loop in the xy plane. Let's say this is x, just for simplicity, and this is y. What I'm going to do is go ahead and do this. I'm going to take a loop all the way around here of a given radial distance. Might as well take it rho. You with me, class? And what I'm going to say is, if I look at this, I know the integral. I know, first of all, you've got to see the symmetry in order to do this. You all see if you have an infinite line of current on the z-axis, that the actual magnitude of the H field will only be a function of the radial distance away from the axis. How many see this? You have to at least see the symmetry. It is cylindrically symmetric, and it won't matter where you are in height if it's infinite. So if you have this, when I go ahead and I write the integral of h dot dl around the closed loop in the counterclockwise direction equal to I enclosed. Really what I mean by I enclosed is how much current penetrates that surface perpendicularly. You all follow me? It has to be, it could be a current density. It doesn't have to be a single thread of current, but it has to penetrate the area that your loop actually carves out perpendicular. So if you look at this, over here, I enclosed is simply I. You all follow me on that? Now, if you look at the other side, the integral of h dot dl, that's really, you all see the H field at a given radial distance will be the same magnitude all the way around. It's very similar to the D field. We made arguments the D field at a given radial distance from a line charge would be the same in terms of its magnitude at a given distance rho. You all remember that? So really what I have is H, when I do this integral, I would get H phi, and it would be times the actual perimeter, which is 2 pi rho. And that means H phi in the phi direction would be I over 2 pi rho in magnitude. Now, that's just going to be the magnitude of this, and I'm going to show you a trick in the direction. I can write down a lot of formal stuff, but this is the easiest way, and everybody does it. You got your right hand. Put your right hand in the direction of current, just as before. Your fingers point in the direction of the H. You see how that's positive A phi? This would be A phi axis. If you look down the Z axis, it's counterclockwise in that direction. Can you all see that? So you can put A phi here. And that's exactly what we talked about at the beginning of the class from an infinite line. Remember that? So That's great for an infinite line. Now, what if happens if you don't have just an infinite line? By the way, most of the things you do with Ampere's law or for something that is cylindrically symmetric, you can do it for a plane of current density, and we'll do that, but this is the normal way. Cylinders are typically that have current density. So now I'm going to go to the next part of this. I think you'll see it. I think you're going to be okay. All right. So the next part is this. Suppose I don't have just a filament of current. Suppose I have something like this. Make sure you write this down. I'm going to make it symmetric with the z-axis, but I'm going to have a wire of radius A, solid wire, and that wire is going to carry a total current of I. Now, this is important. You watch this. So the wire itself has a total current of I flowing. Everybody with me? You all agree that would be cylindrically symmetric. Assume it's evenly distributed over the surface of the wire. Got me on this, class? Now, when you have a problem like this, the step you need to do is get the current density in. This is important. So how would you get the current density in here, J? Remember, that's really what? It's I over the area that the current's flowing through if it's uniformly distributed, and it would be in the direction it's flowing. This would be AZ. You all follow me? I'll write down what it is in a second. How many see this right here? You good with it? Far back? All right, so for that one, J would be a vector. I is just I. What is the area? Remember, it's the cross-sectional area. What's the cross-sectional area that current's flowing through, class? Pi a squared. Do you all hear that? Everybody? Pi a squared. It's the cross-sectional area. It's the area of that plate, you might say. So it's over pi a squared, and this would be in the AZ direction. The units of this would be amps per meter squared. Everybody with me? Can you all see it in the back there? You good? All right. Now, when we apply Ampere's law to this problem, I'm going to look down the cross-section of that. Assume you're looking right down the z-axis. Call this x, call this y. I'm going to try to show you this. When you look at this, you have a current density in here, and it's flowing, let's see, x, y, it's flowing out of the board, right? You're going to have a current density J here, and again, J would be this value coming out. But out here, once you get outside where the wire exists, this would be a radius A here. Then you can see J outside there would be 0. Do you all follow me? It's contained within the wire's radius. You with me? How many see this right here? Got to make sure everybody sees it. Good? All right. Now, if you use Ampere's law to solve for the H field anywhere, we want the H field in at any radial distance. That's what we're at. We go ahead and we use the form, the integral of H dot dl around the closed loop is equal to the current flowing inside that loop. Now there's two possibilities. One is the radial distance is going to be less than or equal to A, and that's the one we're going to do. That means we're inside here. We're at some radius here, and we're going to do this. Y'all follow me, class? Be attentive here. Now, when you look at this, the integral of H dot dl is always going to be the perimeter, which is 2 pi rho. You all follow me? That's the circumference times h feet. This will always be. So it's going to be 2 pi rho times h feet. But now, how much current is actually penetrating that loop right there? Class? Well, you could write an integration. Take J ds and integrate it, right? But what does your gut say? If we have the current density in amps per meter squared, and it is a constant, can't we just multiply that current density by the area of that loop to get it? How many see this? You see it or not, sir? All right, think about this. If you have the current density is amps per meter squared, right? we know if we were out to the edge, all the current would flow there, right? If we're inside here, we want to know how much current would flow. It would be the current density, I over pi a squared, times what? Rho, it would be rho squared times pi. Wouldn't it, class? That would be the area there. So over here, you just put this, the amount of current flowing there would be I, and technically it's over 2 pi a squared, but then it's times, pi a squared, my bad, times pi rho squared. And you can see that's really going to be I, it would be rho over a squared. And then to get h phi, you simply divide that by 2 pi rho and you get I over 2 pi rho, and it's a squared amps per meter. Can you all follow me? It would be in the h phi direction, by the way. With me, class? How many see this? All right. Now, what happens when we get, and this is an important point, when we get outside, when rho itself exceeds A, and I'm out here, rho now is going to be greater than A. That would be a second part. I'll put it over here. When you say that rho now is greater than A, this is still the form you have to solve. It's the integral of H dot dl around the closed loop is equal to I enclosed. Right? But how much current now, if you're outside the radius A, how much current is flowing through my loop out here? Class? I, all of it, right? Think about that. What you're trying to do is I've got something, try to understand this. I've got all this current I here flowing at a radius A. Now I'm coming out and I put a loop all the way around there. If you think about the cross-sectional area of that loop, all the current flows through. Doesn't it, class? Not just, it's not zero. Zero is after A, there's no additional current. But now that means over here, it's straightforward. This is 2 pi rho times h phi. And over here, you just have all the I. So you can see when you're outside that radius, it's like a simple straight wire with that current, I. And it means h phi here is just equal to I over 2 pi rho a phi. Follow me? What does it plot? What does it look like? I always ask people to sketch things, especially on the final stuff. So if you were to plot this, what would it look like? Well, at rho equals 0, this is rho in this direction. What is it at rho equals 0? That's when we're here. Right? What is it, class? Just do it. It's 0, right? It's as obvious as can be. It's 0. Starts at 0, and what happens? It's going up linearly as rho, doesn't it? Then it hits the edge here, and then it starts falling off as 1 over rho. And this peak value would just be I over 2 pi a. How many see this here? All right, I'm going to talk more about that later, but I'm going to give you a quiz. And I want to tell you one other thing about this. If you come to the next week of classes for the magnificent, actually do your homework and keep up, you're going to be very well off with this stuff because I'll try to make this clear as possible. Don't mess around now because it gets more complicated, but I'll try to make it clear.